Okay, this is my second attempt at this problem, so hopefully I won't mess it up this time. There was an issue in my last proof, but I fixed it. So let's go. If alpha is in, so we're going to prove that an is normal in Sn. And okay, so n sigma and Sn. Okay. Then we know that the sign of alpha is 1 because that's what it means to be an AN. The sign of sigma is going to be either 1 or -2. No, wow. Okay, no, 1 or -1. If it's -1, then the sign of sigma alpha sigma inverse equals sine sigma, sine alpha, sine sigma, and the inverse we can pull it out because sine is a homomorphism. So this is 1 times 1 times 1 inverse, which is equal to 1. So in this case, sigma alpha sigma inverse is in AN. By the way, sorry about my handwriting. I'm trying to write without having my forearm or wrist resting on the tablet, and because apparently that if your wrist and forearm are hovering, then it's better for your hand and you don't get cramps, but it makes it harder to write with more precision. So anyways, then we just do the you know what? Here's a cool trick. Let's do, if sine is plus or minus 1, then this is going to be, here we have plus or minus 1, and here we have plus or minus 1. Let's rewrite that, plus or minus 1 to the inverse. And of course, taking the inverse of plus or minus 1 is not going to change it at all. And so we're going to end up with 1. And so then this, and hence AN is normal in Sn. So there we go, that's part A. So now we want to move on to B. So suppose n is greater than or equal to 5. And of course this is going to rely on the fact that AN is trivial when n is greater than or equal to 5. That's really the foundation of this argument. So let n be a normal subgroup of Sn, then n intersect AN is going to be normal in AN. That's because if you look at the conjugation-wise definition of normality, then what we're doing is we're just restricting to subgroups, and so the normality conditions they still hold. Oh, wait a minute. Is that necessarily true? Well, yes, it is, because the fact that this n intersect AN, this guarantees that n intersect AN is a subset of AN, and the fact that conjugation by elements of here, conjugating by an element of Sn will give us an element of AN. And so yeah, that's exactly, the results from the first paragraph just give us this basically. Okay, so by simplicity, we have n intersect AN equals AN, or n intersect AN equals just E. So we want to consider cases where n is non-trivial. So let's consider the first case where n is intersect AN equals AN. And since we're looking for non-trivial, or since we're trying to find examples of n which are non-trivial and not AN, then So if this and if n is not, oh God, I cannot write with this. It'll definitely take some getting used to for me writing like this. So if n is not equal to an, then it contains an, and further, not only does it contain an, but it must contain some element that's in Sn but not in an, because otherwise it'd be equal. So it must contain some odd permutation. Say gamma 1 through gamma n, where each gamma I is a transposition and n is odd. See here. Then if we look at gamma n inverse all the way up through gamma 2 inverse, this is an even permutation because n is odd, so this is even, and so this is contained in a n, of course, which is a subset of n. So gamma 1 through gamma n times gamma n inverse all the way up to gamma 2 inverse, which is so gamma 1, we can write this as gamma 1 through gamma n, then gamma n inverse through gamma 2 inverse, because the gamma 2's and through gamma n's will cancel when we take this product. But look, we're taking the product of two things in an. No. The product of two things in n. And so this must be an element of n. So we have this particular transposition, gamma 1, that we know is contained in n. So say gamma 1 equals AB. Then for any transposition, we'll call it CD, then CD AB is in AN, which is contained in N. So CD, which we can write here, let's put it like this. We might be able to fit the rest of this argument. So CD, we can write this as CD times AB, because AB is AB inverse. And so this is in N, or here, let's make this explicit. So to make it clear that we're multiplying two elements of N together. Thus, and so every single transposition in Sn belongs to N. And that means that N is equal to A, no. Thus N is equal to Sn. Wrote that down wrong when I was writing this out. Okay, so what have we proven? Let's see here. So, so if n intersect an equals an, this implies that either n equals an or this whole other argument we had proved that n equals Sn. Okay, so that's good. That means that we're so far we're on the right track to proving that the only the only normal subgroups are 0, Sn, and An. Okay? So that's this part. So this was a situation where n intersect An is equal to An. Now we have to consider when n intersect An is equal to E. Okay? So if n intersect An equals E, then so certainly n equals E is an option here. That would certainly satisfy this equation, and n would be a normal subgroup in that case. So we're going to assume for contradiction that n is not equal to E. Let's see here. So if n intersect An is E, then n cannot contain any other element of An besides E, which means then n contains no even permutations other than the trivial one, E. Okay? And n contains, well, if n is not equal to E, then it must contain some element that's not E. And, well, that element can't be E, and it can't be an even permutation. And so n contains at least one odd permutation. So now we're going to do kind of like we're going in dangerously into PDE territory here, because we're going to prove we've proven existence, and now we're going to prove uniqueness of this odd permutation. So let sigma 1 and sigma 2 be two odd permutations in n. Be two odd permutations in n. Let's see here. Sigma 1 squared and sigma 1 sigma 2 are even, because if you take, because an odd times an odd is an even, so two odd permutations multiplied together gives you an even permutation. But they're even elements of n, because n is a subgroup. So sigma 1 squared equals E, which is equal to sigma 1 sigma 2. But then we cancel sigma 1 on the left, so we get sigma 1 equals sigma 2. Thus, n is precisely E sigma, where, let's see here, where sigma is some odd permutation such that sigma squared equals E. I'm starting to get a little bit of a hang of this whole writing without resting my arm on the tablet. So let's hope that this continues. So let us write sigma, we'll call it gamma 1 through gamma n as, or rather j because we used n already, as a product not of transpositions but of disjoint cycles. Okay, so but now this is actually really interesting, because sigma squared equals, this is actually sort of tricky, and I'm actually sort of neat, like there's a lot of things with me doing all these algebra problems this summer. There have been a lot of things where it's just like, oh, I get stuck and I have absolutely no idea what to do. And so I succumb to looking online to getting hints on how to move forward. And then I see something and it's just like, oh, I see how that works, but I have no idea how I would have come up with that. But this, I actually, okay, well, a lot of these outlines I did actually find online. But this particular part was a part that I had to iron out some of the details for myself. And so this is actually something that I noticed in doing this, and so this is actually cool. So if we have sigma as a product of disjoint cycles, and sigma squared is equal to E, then if you think about it, if any one of these disjoint cycles had more than 2 elements, then applying it twice would not get you back to where you started. And so it wouldn't be the identity action. And therefore, since sigma squared equals E, each, come on, I'm having a moment here. Don't break on me. So then each gamma I must be a transposition. And that's useful, because now we have sigma as a product of disjoint transpositions. So say gamma 1 equals AB. Let C be not equal to A or B. Then AC sigma AC inverse. What is this? Well, this is just AC applied to AB, and then we've got gamma 2 through gamma J. Then we've got AC again, because that's what AC inverse is. And what do we know about this? This sends A to C. Ooh, wait a minute. Yeah, because A will go to C here, but then C will go back to A. That's not quite right. This sends B to C. There we go. Because if we start out, B is not in AC, and B cannot be in gamma 2 through gamma J because all the gamma I's are disjoint. And since B is in gamma 1, B cannot be in gamma 2 through gamma J. Okay, so B, when we're looking through this permutation and seeing where B goes, moving from right to left, of course, because permutations are weird like that. The first thing that happens is we get to A to B, and B gets sent to A, and then at the next transposition, A gets sent to C. And so we have B getting sent to C in the end. And so this permutation, I guess it would have been faster to write out AC sigma AC inverse. It could be neither E nor sigma, because it's certainly not E, because it sends B to something that's not B. And it's not sigma because sigma sends B to A rather than to C. And we chose C to not be equal to A. And this contradicts. What does this contradict? We're conjugating here. We're taking an element of n and we're conjugating it by just some element of Sn. So this contradicts n normal and Sn. So thus if what do we have? Going way back, thus n intersect an equals E implies that n equals E. Hence, what does this mean? This means that if we looked at all possible possible scenarios for what n could be, and we found that n could be either E, it could be an, or it could be Sn. So hence n normal in Sn n not equal to e and n not equal to Sn implies that n must be equal to an for n greater than or equal to 5. And that's exactly what we wanted to prove in part B. Okay, now we're finally ready to prove part C, which I now have forgotten, and I threw out the sheet that I had this on because this was the last problem that I had to do on this particular sheet. But thankfully it looks like if I just start writing out stuff, I'll find where I am. So finally, finally I claim that S4 contains a normal subgroup besides A4. And of course I mean a non-trivial normal subgroup, but now that my computer is starting to go pretty slow, I don't want to erase things and write in things if I don't have to. So yeah, this is what we wanted to do in part C. Thankfully I actually wrote it down in this solution. So recall that H, given a subgroup H of G, this is normal if and only if H is a union of conjugacy classes. And that's just a group theory fact. Scroll down a little bit more. See classes. And recall also that, what else do we know? What do we know about the conjugacy classes in Sn? The conjugacy classes in Sn are given by cycle decomposition structures. So for example, the collection of transpositions is a conjugacy class in Sn. The collection of permutations which can be written as 1 3-cycle is a conjugacy class. The collection of permutations which can be written as a product of 2 disjoint 2 cycles is a permutation type, and so on. Let's see here. So now what do we know about A4? A4 contains E, also contains permutations. Well, actually, let's not even do this. It contains E, and I'm not going to worry about if I'm going to show all of A4 here, but it certainly contains permutations of cycle type A, B, C, where A, B, and C are indices between 1 and 4. And why is this? This is because we can write this as BC, AC. So there is one way to write any such cycle, any such 3-cycle as a product of an even number of transpositions, and therefore every decomposition into transpositions gives you an even number because the sine function is well defined. That's how we define the sine. That's how we were able to define the sine function in the first place. Okay. So to find another thing. So let H contain E and all permutations of cycle type A, B, C, D. So then H is going to have E in it. It's small enough that we can just write it out. It's going to have 1, 2, 3, 4. It's going to have 1, 3, 2, 4. And it's also going to have 1, 4, 2, 3. See here. If H turns out to be a subgroup, then since H is a union of conjugacy classes, it will follow that H is normal in S4. Because remember, that's an equivalent condition for having for a subgroup to be normal. See here. So denoting H as being, let's see here, we'll have E, and then we'll have sigma 1, sigma 2, and sigma 3. Then one can check. I'm not going to do it because it's really, like, there's really no calculations that you do. You just look at it, and then you see, oh, it does exactly what I say it does. So anyways, one can check that. Let's see here. Sigma I times sigma j equals sigma k, where I, j, and k are distinct elements of the indices from 1, 2, and 3. So now that I'm looking at this is sort of weird because you could sort of associate this product, like you can take like a permutation of 1, 2, and 3. You can take a permutation of S3 and use it to like define this equation that you are proving that you hold. So you can, like, I don't know, it's kind of weird. You can study permutations using permutations, which kind of makes sense because pretty much anything to do with finite groups, you're dealing with permutations because every group is a subgroup of a permutation group. That's a fact, which I'm sure you know at this point. Or if you don't, that's all right, but you should learn it because it's cool. So I, j, and k are distinct elements of 1, 2, 3. Okay? So but we know that H does not contain since H does not contain let's say 1, 2, 3, which is contained in A4. This is not very standard, but I'm writing it anyways. Then H is not equal to A4. Hence, A4 is not the only non-trivial normal subgroup of A of S4. And so there we go. This is what we wanted to prove. And an interesting question is, you might look at this example and think, what happens when n is greater than or equal to 5? What happens to this h that we've constructed here? And that is a fantastic question, but I did not think about it because it wasn't part of this question, and I don't really have the time right now to think about algebra problems that I don't need to be working on to study for stuff. I mean, of course, you could always make more time to study it. I just didn't think about this, or didn't think to make time to think about this. But it's worth understanding and worth thinking about why this example. This example of using, you might think like, how did I come up with this? Looking at these like 1 2 3 4, 1 3 2 4, 1 4 2 3, looking at these disjoint products of transpositions, like why would I think of that? This is actually the reason. This is actually sort of a common subgroup of A4 to look at. It typically when you talk about permutations, this particular subgroup of A4 will come up at some point. I know it comes up in Artin's book Algebra. And that's useful because that's more. I think that's more of a advanced undergrad textbook, and so that's very likely to be like your first time seeing an algebra textbook, and so it's good that he includes like important examples of subgroups in there. I don't quite remember if Jacobson spends a lot of time talking about it. My guess is that if this comes up at all in Jacobson, it will like come up in an exercise, because Jacobson tends to not fill his textbook with too many examples or discuss too many examples that are like, he tends to be more on the abstract end of things, which isn't bad. It's just what it is. Okay, but anyways, that's just me babbling at the end of the solution, which I tend to do, and so we're done with this exercise.